Welcome back. Let's continue with our backpropagation example. Don't forget to enroll in the free Udemy tutorial Vehicle Suspension Control 4 PID Tuning with AI TD3 in order to gain access to the code files and the explanations related to this mini course. The link is in the description. Also note that the free coupons that I offer for that, they have limitations in terms of time and the number of enrollments. However, don't worry, I will be renewing them periodically. We have our network in which we now also apply the sigmoid activation function. We have the input values 0.1 and 0.2. We also have the desired or target outputs 0.05 and 0.95. I will now add the subscript T to indicate that these are my target outputs. The goal now is to find the required weights and biases to make sure that the given inputs applied to the network would at least approximately give me these target outputs. I will first initiate these weights and biases with some values chosen by me. I'll choose 0.2 for all the initial weights and 0.3 for all the initial biases. In other words, we will initiate the network with these values. We can use them to calculate the outputs. This is called forward pass. We will be using the same 4 stages as was shown in the previous video. Only now, of course, when we initiate our weights and biases with some values, our outputs at the beginning will not be these values. These were our target values. We will initially have other numbers for the real outputs. And so, let's start computing O1 asterisk and O2 asterisk given these inputs. This will be our first step. Here are the weights, here are the biases. This is the input. After performing the calculations, I will get this vector for the hidden layer. In this particular case, since both elements are the same here, in the second step, I will simply write h1 asterisk equals h2 asterisk and the activation function. This one here, that's h1, which is also h2. It will approximately give me 0.589. Then in the third step, I need to calculate O1 and O2. This is the weight matrix. This is H1 star and H2 star. And here I have the biases. As a result, I will get this vector. And then finally, I need to activate the output neurons as well. And I will do it with this function. Since both of my O's are the same, I only need to write this function once, because these two variables are equal, and in the end, I will get this number for these two activated neurons. With these 4 steps, we've completed the forward pass. We propagated forward through the network. The outputs that we got in the end are these ones. However, our desired or target outputs are these ones here, 0.05 and 0.95. Since my current activated outputs and the target ones are not equal, I can write an equation that would be my error or loss function. So error total equals the error for the first output neuron plus the error for the second output neuron. These errors will not be simply the differences of these numbers. Instead, I will choose my error function to have this term plus this term. This one here, it's this one, and then this term here, it's this one. I first calculate the differences between what I want and what I actually get from my network. I will then square these differences. I have the power of 2 here and also here. The reason why I square them is because I don't care about the signs of these differences. In addition, when I square them, I will also make sure that both terms are positive and the errors in one term do not cancel the errors in the other term. If I simply had this difference plus this difference, then if, for instance, this one is minus 5 and this one is plus 5, then my total error would be minus 5 plus 5 equals 0. And so it would seem that I have no error, but that of course is not true. I have errors in both terms, it's just they cancel each other out. But that's not good for me, because what I need is for this guy to approach this guy, and this guy to approach this guy. In other words, I need this difference to be 0, and this difference to be 0. When I square both differences, then both terms will be positive, and when the total error is forced to approach 0, it will inevitably mean that both of these terms and these differences will also be forced to approach 0, which is exactly what I want. If I achieve that, then the given inputs at the entrance of my network will give me the desired outputs. Of course, I could have also used the absolute values, but the problem would be that it's not differentiable everywhere. This would be your absolute value function, but the point where the function suddenly changes does not have a defined derivative. On the other hand, a squared function does not have that problem. It's differentiable everywhere. And since we're going to have to differentiate the error function with respect to the weights and biases, it's better to choose a squared function for the error. I also put the constant 1/2 here and here as well. This is simply for convenience. When I differentiate a squared function, which looks like this, then I will have this convenient form. This 1/2 constant does not play any role in backpropagation, whether you have it or not. In both cases, you want your total error to approach 0, and it will approach 0, which means that in both cases, whether you have this constant or not, your real outputs will converge on the desired outputs. So it's really just a convenience thing. And now, in order to train the network, in order to find the weights and biases that drive this error to 0, we have to know how this error changes with respect to them, with respect to the weights and biases. In other words, we want to know the gradient of the total error. We can denote this gradient like this. That gradient vector is a vector that contains the partial derivatives of the total error with respect to the elements of this weight vector, which I denote like this. This weight vector, it contains all the weights and biases that we have in this network here. I transpose this row vector in order to indicate that this is in fact a column vector. In order to write column vectors more compactly, it is very common to write them as row vectors and then transpose them. And so, this is simply a compact way of describing this gradient vector. You can see that you are taking the partial derivative of the total error with respect to each element that is inside this vector here. Now, differentiation means change. Therefore, this gradient vector contains information on how the total error changes with respect to every weight and bias. I can use this gradient vector to adjust this weight vector to drive the total error to 0. Remember, we want this error to approach 0. And in order to achieve that, I will use a simple gradient descent method that looks like this. There are several gradient descent methods out there, but this is probably the easiest one. This gamma here, that's the learning rate. It regulates by how much the weights change every step. If it's too small, learning will be too slow. If it's too big, there will be too much overshooting in the learning process, and the algorithm might fail to converge. There is an optimal value for gamma that you often have to find through trial and error. We will set it to 0.5 as it works reasonably well in our example. Now, why does it work? How is this gradient descent algorithm able to adjust the weights and biases in such a way to drive the total error to 0? Imagine that I have this parabola, so I have my total error as a function of some weight. Now let me be very clear about something. In reality, the relationship between the error and the weight is much more complicated than this parabola, because you have activation functions and you have several layers in the network, which means that you have several activation functions, so the real relationship between the error and the weight is going to be much more complicated. However, for intuition purposes, I will assume that the relationship is parabolic, because that way I will still be able to convey the general idea behind this gradient descent method to you. So let's just make this super naive assumption that the relationship between a weight or a bias and the total error is parabolic. It's not the truth, but this video is about intuition anyway. If I update my weight in this way, then first of all notice that from the location where my total error is minimum, which happens at wi asterisk, if from that point wi becomes greater than wi asterisk, then your total error will also become greater. And the more positive this wi becomes from this optimal point, the greater the total error will be. Similarly, the more negative wi becomes from this optimal point, the bigger your total error. Now you of course want wi to converge to wi asterisk, because in that case your total error will converge to 0. It means that if you are on this side, you want wi to decrease, and if you're on this side, you want it to increase. When you take the partial derivative of the error with respect to this weight, then you get the slopes of the function, which represents how the error changes with respect to that weight. Here you have positive change, and here you have negative change. And so, on this side, you can clearly see that this change is positive, which means that this equation will decrease the weight, bringing the error closer to 0. And that's because you have a minus sign here, and the derivative is positive. On the other hand, on this side, the derivative will be negative, but you also have a minus sign here, and the two minus signs will give you a plus sign, which means that this equation will increase the weight, bringing your total error closer to 0. As you can see, this gradient descent equation gives me exactly what I want on both sides. On the right side, it decreases the wi, which is what I need, and on the left side, it increases it, which is also what I need. And you can imagine that for every weight and bias, you have that relationship where you have your total error written as a function of that weight or bias. There is an optimal value for all of the w's and b's, and once you reach all those optimal values, your total error will become 0. We can even look at this made-up function here, y as a function of x. This is some complicated relationship here, but notice that you still have a minimum point here, y min, that corresponds to x asterisk, and so when you're on the right side, you want your x to decrease, because then you will approach x asterisk, which means that y will approach y min. And then on the left side, you want x to increase, because that's how you will approach the optimal x, and y will approach y min. And this equation will work because on the left side, this derivative is negative, and on the right side, it's positive. Of course, one big limitation with this gradient descent method is that when you have something like this, then you have several minimum points here. You have the global minimum, but also local minimum. And the danger here, of course, is that you can get stuck in some local minimum point, because when you are on this side, you have a negative gradient, but then in this region here, on the left side of this orange line, your derivative is positive, and so if you apply this equation here, your x will increase here, but it will decrease here, and you might never reach your global minimum. This is a big problem with nonlinear systems in general, and also when you train your neural networks, you can face similar problems, which is why, in reinforcement learning for instance, you have this notion of exploration versus exploitation. Do you go with what you have already learned so far, or do you explore in order to maybe find something better? There is an active research going on to tackle these local minima problems. Also, the opposite of gradient descent algorithm would be the gradient ascent algorithm. In this case, you would have plus here, and then everything would be in reverse. You would be looking for the maximum point that would happen at x star max, and so on this side, you would have a positive derivative, then on this side you would have a negative derivative, and to find the maximum point, when you have a positive derivative, you want your x to increase, and when you have a negative derivative, then you want your x to decrease in order to converge to this x star max. And this gradient descent algorithm, because of this plus sign, will make it happen. When your derivative is positive, so you will have a plus sign here, then your x will increase, and when your derivative is negative, then plus and minus will give you a minus, so your x will end up decreasing, getting closer to x star max. And it all makes sense because when you have a positive derivative, that means that increasing x will result in increasing y. And so, if your goal is to increase y and find its maximum, in the case of a positive derivative, you want to keep increasing x because you know that it will also increase y. But if your goal is to find the minimum value of y, then you want to do the opposite. You want to decrease x because that will also decrease y. And then similarly, if you have a negative derivative, then you know that in case of a negative derivative, if you increase x, that will cause your y to decrease. So if you want to find the minimum of y, then you want to keep increasing your x because you know that it will decrease your y even further. However, if your goal is to find the maximum of y, then you want to do the opposite. You want to decrease x because you know that it will cause y to increase. You want to make x smaller because you know that it will make y bigger, getting you closer to its maximum value. Once you have the gradient vector, you can run this equation thousands of times until the weight vector approaches the optimal weight vector, and that's when your total error approaches 0. And when that happens, the outputs of the neural net will approach the desired outputs. And this technique to train the network is called backpropagation. The next step will be to actually find the partial derivatives and thus the gradient vector. We calculated the outputs using forward pass. However, to compute the gradient, we will have to move backwards. This is called backwards pass. In the next video, we're going to find them manually. Now, just to let you know, in reality, no one computes them manually. Libraries like PyTorch do that automatically. Also, for large networks, doing it manually would be impractical. But we're going to do it once on this small network to get intuition for it. In fact, I will leave it to you as an assignment. Try finding the partial derivatives yourself first, and then check your answers with me in the next video. Thank you.